Lesson 3.3, Rules for Differentiation. We're going to learn how to find the derivatives of positive integer powers, multiples, sums and differences, products and quotients we'll do tomorrow. We'll do some negative integer powers of x, definition of e, derivative of e to the x, and some second and higher order derivatives as well. Okay, so if you're in class, you're doing this as an opener, consider the following table, fill in what you know given the information that you have. Looking at these three here, this should give you some hints as to what you'd expect for f of x equals x to the fifth. The derivative of that would be 5x to the fourth. And what you'll notice is that if I have x to the second as f of x, the 2 comes down in front and the power reduces by one integer value. So x to the fifth becomes 5x to the fourth. So x to the nth power, in this example here, x to the nth would become n times x to the n minus 1. Okay, each of these is an example of a rule called the power rule. The power rule. Sums and difference rule, as you'll see here, h of x equals g of x plus f of x. So h prime of x is equal to g prime of x plus or minus, depending on whether it's a sum or a difference, f prime of x. So you can just take the derivative separately. And this last example here is awesome because e to the x is the best. The derivative of e to the x is actually itself. We just call this the e to the x rule. So for a moment, let's backtrack here and go back to the first two examples here. F of x equals c, if c is a constant, is actually the derivative is 0. If you think about a graph where f of x is always, whatever c, let's say c is a positive integer, well, the slope on that curve would always be 0. Okay, and this example here, f of x equals mx, the derivative of that would be m. All right, on the same line, right, if I have mx, let's say I have 2x. What's the slope on that entire function? Well, it would be 2. So if that equals mx, then its derivative equals m. And I don't really have a special rule for those. I'm just gonna go with that as is. Okay, so that's a nice intro there. Let's move on. All right, so let's find some derivatives. Why don't you pause the video and do the first 4 and come back and see if you got them right. All right, so I've performed each of these derivatives. If a polynomial like 1 and 2 are in standard form, or at least in a form that has been expanded fully, you can use the power rule. However, in 3 and 4, I had to actually FOIL before I could use the power rule. So here you can see I brought that 5 down in front and went 3 times 5, and then took the power of 5 and subtracted 1. So my derivative would be 15x to the fourth. Derivative in the second one is negative 16x to the seventh. The trick in the second part is that we are, again, subtracting 1 from this power of negative 9 to make that negative 10. Some of you might have had a negative 8. Be careful with that. Likewise, down here I get a derivative of 12x minus 11 and 50x minus 80 for number 4. Go ahead and pause the video again, and actually let me scroll down here a little bit and do number 5, 6, and 7. Okay, here we are, number 5. First thing I would do to expand this, multiply this one term, negative 3x to the fourth, to each of the individual terms in this trinomial. I'd get the following, and then when I took the derivative, right, I get negative 36x to the 11th. I took this negative 9x to the 6th, which becomes negative 54x to the 5th, and I moved that in front to keep this in descending order for each of these powers. Okay, trick on number 6. Okay, we get 4x to the third, as you'd see. We get negative e to the x. That's just the derivative of e to the x is itself. But e times x, the derivative of that, like we had in the original slide in the beginning, would be e. That would be the derivative of that term. Okay, here I did a little trick. I split this into 3 terms, dividing each of those 3 terms by x squared. So 3x to the 9th over x squared is 3x to the 7th. Negative x squared over x squared is negative 1. And then 5x over x squared is 5 over x. Okay, I did a little algebraic manipulation here and turned that into 5x to the power of negative 1. And you'll see that our derivative here is 21x to the 6th minus 5x to the negative 2nd, or you could rewrite it as negative 5 over x squared. Okay, so let's talk a little bit of notation for higher order derivatives. Here's the first derivative, right? Here's your second derivative, and here's your third derivative. Okay, here's your f notation for each of those. The ddx notation for each of those is pretty similar. One way to write the ddx notation would be dy dx, right? That's the derivative of y with respect to x. That's for the first derivative. The second derivative is d squared y dx squared. That's just an indicator of the second derivative. And the third derivative kind of follows suit with that. That's d cubed y dx cubed. Okay, so those are your derivative notations in f notation and ddx notation. So let's find the second derivative of the following. I'm going to use this y notation for a minute. Okay, so first let's do d dx of this function y. Well, that would be 8x to the third minus 6x to the first. The 7 drops off. So that's dy dx, right? So dy dx equals this. Okay, now let's do the derivative again. So let's take d dx of dy dx. And what do we get? Well, if we take the derivative of that, we get 24x squared minus 6. So notice now we have d squared y dx squared. Okay, and that is our second derivative. Okay, let's move on to a little AP problem. If f of x equals the following, what is f prime of 2? Well, let's find f prime of x first. F prime of x will equal 3x squared minus 2x plus 1. So f prime of 2 will equal, that'll be 3 times 4, which is 12. That'll be minus 4 plus 1. So f prime of 2, the slope of the graph at x equals 2, looks like it'll be 9. Okay, let's look at this example, another AP problem. Let f be the function, f of x equals that. What is the instantaneous rate of change of f at x equals 3? That's asking us for f prime of 3. So let's find f prime of x. F prime of x would be 3x squared minus 12x plus 8. F prime at 3 would be, looks like 27 minus 36 plus 8, which, if I'm not mistaken, would be negative 1. Okay, let's analyze the following AP problem. Okay, this is interesting now. We're given a graph up here of the derivative. Okay, and we're given a bunch of graphs of our potential f functions, our original functions. So it says the figure above shows the graph of f prime, the derivative of the function f. If f of 0 equals 0, which of the following could be a graph of f? Okay, so a few things I want to point out. Right here and right here and right here, the derivative is 0, which means that there is no slope. There's a slope of 0, which means the graph has either hit a maximum value or a minimum value at 2 and 3 and 4. So let's look at min values and max values at 2, 3, 4. Okay, I'm seeing this function here has max values at 2, 3, and 4. However, it also has a max value at 1. Since our derivative does not show a derivative of 0 at that graph is out. Okay, I see a max value here somewhere between 0 and 1, somewhere between 1 and 2, and somewhere between 3 and 4. That graph is out. Okay, I see a max value here at 1, at 2, at 3. We know that there was no max or min value at 1, therefore that graph is out. And this graph here, D, looks like a max value at 2 and 3, but it doesn't have a max or min value at 4, therefore that is out. So in this case, it looks like C is our answer. Let's just check for a moment. It's got a max at 2 and at 3 and at 4. Let's analyze a little bit of other stuff on this graph. Looks like between 2 and 3, because the derivative is negative, that means the graph should have a negative slope. Let's see if that matches, and it does. Between 0 and 2, the graph has a positive derivative, and between 3 and 4, it also has a positive derivative. Therefore, the graph F should be increasing between both 0 and 2, and as well as 3 and 4. So I think we can, validate the fact that C would be our answer here for F. So that'll be it for today, folks. That's 3.3 on derivative shortcuts.